Have you ever wondered why sodium reacts so dramatically when it touches water, bubbling and fizzing, while neon stays completely calm and unreactive? The answer lies in something called ionization energy. It's a simple but powerful concept in chemistry that helps us understand how tightly an atom holds onto its electrons. This affects how elements react with each other and explains why some are highly reactive, like sodium, while others, like neon, are stable and don't react easily. Today, we'll take a closer look at ionization energy, what it means, and how it influences the behavior of atoms across the periodic table. By the end of this journey, you'll have a clear understanding of what makes each element unique and how the forces inside an atom shape the world around us. Ionization energy is the minimum amount of energy required to remove an electron from a neutral atom in its gaseous state. Imagine pulling a magnet away from a steel surface. The closer and stronger the bond, the harder it is to pull away. That's ionization energy in action. When this happens, the atom forms a cation, a positively charged ion. The ionization energy tells us how tightly an atom holds on to its electrons, and this varies across the periodic table. Let's start with atomic radius. This is the distance between the nucleus of an atom and its outermost electrons. In smaller atoms, like fluorine, the electrons are held closer to the nucleus. This creates a stronger pull, making it harder to remove an electron. As a result, these atoms have high ionization energy. Now, as the atomic radius increases, like in larger atoms such as cesium, the outermost electrons are much farther from the nucleus. This weakens the pull from the nucleus, making it easier to remove an electron. That's why elements with large atomic radii have lower ionization energy. The nucleus is like the powerhouse of the atom, filled with positively charged protons. These protons create a strong positive charge that pulls on the negatively charged electrons, keeping them in place. The stronger this nuclear charge, the harder it becomes to pull an electron away. As we move across a period in the periodic table, the nuclear charge increases. This makes the atom's pull on its electrons stronger, raising the ionization energy. Think of it like turning up the power of a magnet. The stronger the magnet, the harder it is to take something away from it. Inside an atom, not all electrons experience the nucleus's full pull. The inner electrons act as a barrier, blocking some of the nucleus's positive charge from reaching the outermost electrons. This phenomenon is called the shielding effect. As more inner electron layers are added, the shielding effect grows stronger. This weakens the pull of the nucleus on the outermost electrons, making it easier for those electrons to escape. This explains why elements lower in the periodic table, like potassium, have much lower ionization energy compared to elements like nitrogen. In potassium, the many inner electron layers block the nucleus's pull, making it easier to remove its outermost electron. In contrast, nitrogen has fewer shielding layers, allowing the nucleus to hold its electrons more tightly. Let's take a look at periodic trends across a period. As we move across a period in the periodic table, the ionization energy steadily increases. Why does this happen? It's because the atomic radius gets smaller, the nuclear charge grows stronger, and the shielding effect remains constant. These factors work together to pull the electrons closer to the nucleus, making them harder to remove and requiring more energy to do so. This explains why noble gases like helium have the highest ionization energy in their respective periods. They hold onto their electrons with unmatched strength, making them incredibly stable and almost completely unreactive. Now let's look at periodic trends down a group. As we move down a group, ionization energy decreases. Why does this happen? It's because the atomic radius gets larger. The shielding effect from inner electrons becomes stronger, and the outermost electrons are farther away from the nucleus. Think of it like a rubber band. The farther you stretch it, the easier it is to snap. Similarly, the farther an electron is from the nucleus, the weaker the pull holding it in place, making it easier to remove. Chemistry isn't without its surprises. Even the trend of ionization energy has its exceptions. One such twist happens between groups 2 and 3. Here, the ionization energy takes a slight dip. Why? Elements in group 3, like aluminum, have an extra electron in the higher energy p orbital. These p orbitals are less stable and easier to remove than the s orbital electrons of group 2 elements like magnesium. This makes it slightly easier to ionize aluminum compared to magnesium, even though you'd expect it to require more energy. A similar drop occurs between groups 5 and 6. Group 5 elements, like nitrogen, have a half-filled p orbital configuration, which is inherently more stable. This stability makes removing an electron more difficult. But in group 6, elements like oxygen have one more electron in their p orbital. This additional electron creates repulsion and reduces the orbital stability, making it slightly easier to remove an electron. These subtle differences in electron configurations explain the exceptions to the trend. So how does ionization energy impact an element's reactivity? It's simple. The lower the ionization energy, the easier it is for an atom to lose its outermost electrons. Take sodium, for example. Its low ionization energy means it can easily give up an electron to form a bond. That's why sodium reacts so energetically with water, releasing bubbles, heat, and even sparks. Now, compare that to helium. Helium has a very high ionization energy, which means its electrons are held tightly by the nucleus. It's almost impossible to remove one, which is why helium doesn't react, no matter the environment. This difference is why elements with low ionization energy, like sodium, are highly reactive, while those with high ionization energy, like helium, remain stable and chemically inactive. Noble gases like helium are so unreactive that they're often called the inert gases. They're perfectly content, just as they are. Ionization energy isn't just a classroom concept, it's a fundamental principle that powers our understanding of chemistry. It explains why elements behave the way they do, from the explosive reactions of alkali metals to the stability of noble gases. This concept also drives the science behind technologies like lasers, plasma screens, and even the colorful fireworks that light up the night sky. Understanding ionization energy helps us design new materials, predict chemical reactions, and innovate in countless fields of science and engineering. Thank you for watching. We hope you enjoyed exploring the fascinating world of ionization energy and discovering what makes each element unique.